Hello, welcome to your next research methods lesson. Today we're going to be talking about correlations, and then we've only got one more research methods lesson to do. So as always, have your textbook, your pen and your paper ready. Your starter is just 9 questions of things that we've covered so far in the Year 2 research methods. So I want you to pause me and have a go at answering them all. Feel free to use your textbooks if you need a little reminder. So question 1, briefly explain what is meant by falsifiability. Falsifiability is the possibility that the statement or hypothesis can be proved wrong. The only way to prove a statement correct was actually to seek to disprove it, so to falsify it. So there's certain theories in psychology, for example, the psychoanalysis theory by Freud, that is not very scientific because we can't prove it wrong. Explain theory construction as a feature of a science. A theory is a collection of general principles that explain observations and facts. They help us make sense of facts and help us understand and predict natural phenomena. Theories can either come before hypothesis testing, which is deductive reasoning, or after, which is inductive reasoning. How do paradigm shifts contribute to scientific understanding? A dominant paradigm is challenged by accumulated disconfirming evidence until we can no longer be maintained. An example of this was Darwin's theory of evolution. So gradually disconfirming evidence accumulates until the paradigm can no longer be maintained, and then it is overthrown and a paradigm shift occurs. What is meant by empirical method? It's gaining knowledge through direct observation or experience. So think about the burgers. We can only know what a burger is actually like if we go and taste it for ourselves. We can't believe what we see in adverts. Outline the criteria that needs to be met before choosing a parametric test. There's 3 things. The data needs to be at least interval level. It must be normally distributed data, and it must have variances which are not significantly different. Give an example of nominal, ordinal and interval data. So there's lots of things that you could have said here. But I've put for nominal football teams because it's categories, ordinal runners in a race because we can rank them from first to last, and interval data could be temperature because the difference between each of the numbers is exactly the same. Suggest why a researcher may choose to use p is less than 0.01 instead of p is less than 0.05. They do this to reduce the possibility of type 1 errors, and it means that we have more confidence that a difference or correlation is real. So they tend to do this in drug testing, for example. Identify the 3 pieces of information used to find the critical value. So 3 things that you need is 1, the significance level. Is it p is less than 0.05 or is it another significance level? Whether the hypothesis is 1 or 2 tails, so is it directional or is it non-directional? And the number of participants in a study, which gives you the N number. When using the Wilcoxon test, is the calculated value greater than or less than the critical value? With Wilcoxon, it doesn't have an R, so the calculated value is less than the critical value. So in any of the statistical tests that we use, if there is an R, then the calculated value needs to be greater. If there's no R, the calculated value has to be less than. I want to go into a little bit of a recap before we start on the new content, because this is all things that you should already know about correlations, but I appreciate it's been a little while. So, question number 1, and you might want to look in your Year 1 textbooks for this, if you've forgotten. What type of graph is used to show correlational data? So just pause me if you need to think about it. So it's shown as a scatter graph. Number 2, what are the highest and lowest correlation coefficients that are possible? 0 is the lowest and 1 is the highest, or -1. Don't be fooled if you see -1, that is just as strong as a correlation coefficient of +1. It just means that it's negatively correlated. There is no IV and DV in a correlation. What do correlations use instead? They use covariables. How would you judge the strength of a correlation just from its graph? So you look at the dots, and if they form a clear diagonal line, then you know that you've got some sort of correlation going on. The closer the dots are, the stronger the correlation. Number 5, suggest 2 variables that might be negatively and positively correlated. An example of negatively correlated data would be the speed of a car and the journey time, because as one increases, the speed of the car, the other one decreases, the journey time. Same with temperature outside and layers of clothing. As one increases, the temperature outside is increasing, the other one decreases, so less layers of clothing worn. With positively correlated data, you could have said the longer that you are on a treadmill, the more calories you burn, because as one increases, so does the other one. And as the temperature goes up, so do ice cream sales. So high temperature, high ice cream sales. Positive correlated data. Now I want you to write and appropriately operationalise null and directional hypothesis for the following. The relationship between age and running speed over 100 metres. Remember, correlations are not looking for a difference, so you will not say difference in your hypothesis. You would say relationship or correlation. And a null hypothesis tells us that there's going to be none, and a directional hypothesis will tell us which way it's going to go. So have a go at that now. For the null hypothesis, you should have put, there is no correlation between how old someone is and how fast they complete the 100 metres. And for the alternative, you should have put, the older someone is, the slower that they will run the 100 metres. Just 2 more questions to go. Number 7, state 2 potential advantages of using a correlational analysis. So firstly, they allow us to ethically study variables that cannot be manipulated. And it can be an initial investigation. And if the result is significant in our correlation, then it can lead to other causal investigations. Because remember, correlation does not equal causation. State 2 potential disadvantages of using correlational analysis. It's what I've just said. Cause and effect direction cannot be established. Just because some 2 variables correlate does not mean that they are causing each other. So just because the temperature increase is making ice cream sales go up does not mean that the temperature increase is causing those sales to go up. There could be other factors involved. And factors other than covariables that may have an impact are not considered, such as maybe Tesco are having a big ice cream sale. What kind of correlation is this showing? Is it strong or moderate? So how we can tell this is here, this gives us our correlation coefficient, and it's given us a value of 99.79. If you can see that, it's very small. So it's positively correlated. As you can see, as one increases, the other one also increases. But we have to consider that something else could be explaining this correlation. It doesn't mean that US spending on science, space and technology is causing suicides by hanging, strangulation and suffocation. What about this one? What kind of correlation is this showing? Is it strong or moderate? So if we look here, I think that says 66 or 56. I actually can't tell, it's very small. But that is a moderate correlation. The previous one, 99, is a very strong correlation because it's near 1. And remember, 1 is the strongest correlation that you can have. What about this one? This again is positively correlated. It's got a correlation coefficient of 94. So again, it's a very, very strong correlation. And the last one, what kind of correlation is this showing? It's showing a negative correlation because as one variable is increasing, the other one is decreasing. But it's a very strong negative correlation because again, it's very close to 1. So we see here our Simon-Cowell chart, which tells us which statistical test we need to use at which time. So which test do you think we're going to be looking at if we're looking at correlations? Well, it's, as I've stated, correlations do not look at differences, they look at associations, looking at this side of the table. Specifically, we're going to be looking today at Spearman's rho and Pearson's R. chi-squared will be next lesson. So we're going to do an investigation, and it's taken from a study by Brosnan, who found that boys with smaller finger length ratio between their index and ring fingers were more likely to have a talent in maths. If you have a low ratio, it means that your ring finger is bigger than your index finger. And there's lots of biological reasons for this, but it was said that it's because of the effect of testosterone, which is associated with reduced finger length ratio and increased numeracy skills. So if we look at our Simon-Cowell table again, which test are we going to do? Firstly, we need to look at whether it's a test of difference or a test of association. We're doing a test of association because we want to find if there is a relationship between finger length ratio and math skills. So it's going to be a test of association, and tests of association always use related design. And now we have to figure out what kind of data is this? What level of measurement are we going to use? Is it nominal? Can we put this data into categories? No, we can't. Is it ordinal? It is ordinal because we can rank the boys in terms of numeracy skills, but it couldn't be interval because we don't know what questions they're getting, and the differences in difficulty for the questions wouldn't be equal, so it wouldn't be interval. So we're looking at ordinal data, which means that the test we need to do is Spearman's rho. Now, in the exam, you'll never be asked to conduct a Spearman's rho, but you may be asked to tell the examiner the steps that you need to take in order to find Spearman's rho. And you may also be asked to find the critical value or the calculated value in terms of replacing certain numbers from the equation that we're going to see, but more on that when we get to it. So step one for the Spearman's rho is that we have to state the hypothesis. So I want you to pause me now and write me for the investigation that we're going to do an alternative hypothesis stating that there will be a difference because there is previous research to suggest it. You don't have to say that, but that is the reason why we use a directional hypothesis. If there have been studies done in the past to say that there is a relationship, then we would always do a directional. Non-directional we use when we don't know which way it's going to go. And then I want you to write me a null hypothesis as well. So pause me and have a go at doing that. So for the alternative hypothesis, you should have written the finger length ratio between index finger and ring finger is negatively correlated to numeracy skills in boys. Research has found that low ratio means that boys have better numeracy skills. So therefore, this is the alternative hypothesis because as one variable is increasing, the finger length ratio, the other one is decreasing. So it's a negative correlation that we're hoping to find. The null hypothesis would be there is no correlation or relationship or association between finger length ratio and numeracy skills in boys. Once we've written our hypothesis, our next step is to place raw data in a table. Now this raw data you will never be asked to make up. It will always be given to you in the exam. So the raw data shows finger length ratio and numeracy score for each person, and it would give you a raw data table such as this one. So on the left hand side we can see finger length ratio here, and then we can see numeracy score here of, obviously this is one participant, this would be the second participant, etc. And then, such as in the Wilcoxon test, what we do is we rank the data, and we rank A and B together. But again, this would be done for you. And the important bit of Spearman's row is to look at the difference between rank A and rank B. And then that difference is squared, which gives you these values. And this value, the sum of all of the differences squared, gives you 261. But it's rare that you would ever be asked to work that out, but not impossible. So if you see this little squiggly line that looks like that means the sum of. So you would just have to add all of these up, which would be fairly simple to do using a calculator. Step 3 is we need to find the calculated value of row. So to calculate this, you need to rank data in column A and column B from low to high, which was already done for you. You'd never be asked to do that in an exam. And then we found the difference between each pair of ranks, and they square the difference and the column up. And this is the formula for finding Spearman's row. It looks pretty scary at first, but when you actually break it down, it's not that scary. We know that N is the number of participants used in the study. We know that this squiggly line means the sum of, and we know that this just means the differences of the ranks squared. So then it's just a case of inputting the numbers, and you could be asked in an exam to input, say, N, or input the sum of D squared. And it gave us the calculated value of minus 0.58, which is showing a negative correlation. So that brings us on to step 4, which is the result going in the right direction? So we just need to eyeball the value that we've calculated and say, does this match our hypothesis? Well, if you think back to our alternative hypothesis that we gave, we stated a negative correlation. So yes, it is going in the right direction. And then step 5, what we need to do is we find the critical value of row. And we do this the same way that we find the critical value for any of the tests, such as the sign test or Wilcoxon and Mann-Whitney, etc. So firstly, what we need to do is we need to look for the significance level, which is P is less than or equal to 0.05. If it's not stated in the exam question, then you can just assume that it's going to be 0.05. Secondly, we need to look at the kind of hypothesis. Is it directional or is it non-directional? Well, I've already, if they've stated the probability at the significance level of 0.05, that it's going to be a one-tailed hypothesis, because for a two-tailed hypothesis, it's not a significance level of 0.05. But you can also go back and look at your hypothesis, which was one-tailed because it was directional. It was telling us which way the results were going to go. We need to look for the N value 10 because there were 10 boys in our study. And now we locate the row that begins with our value of N for 0.05 significance level. Remember that the calculated value was minus 0.58. Our critical value is 0.564. Remember the importance of R. If any statistical test has an R in the name, such as Spearman's row, then the calculated value has to be greater than or equal to the calculated value. Our calculated value was minus 0.58 and our critical value was 0.564. So the importance of R, the calculated value here has to be greater than or equal to the critical value, which it is. Even though it's a minus, we can ignore that because that's just telling us the way that the correlation is going. So it is greater than the critical value. Therefore, it is significant. So then we write as our conclusion, which you could also be asked in an exam, as the calculated value, you might want to put that in, which was minus 0.58, is significant. We can reject the null hypothesis and accept the alternative hypothesis and conclude that finger length ratio between index finger and ring finger is negatively correlated to numeracy skills in boys. Now we're going on to look at the parametric test of association, which is Pearson's R. And we use Pearson's R when we want to assess the level of inter-rater reliability. So basically, how much two observers agree with what they are observing. So I want you to do the same thing that you did for Spearman's row, and I want you to state the two hypotheses. So I want you to write me an alternative hypothesis and a null hypothesis. The alternative hypothesis should have said something along the lines of the observations from observer A are positively correlated to the observations from observer B. So as one observer sees something, so does the other one, so they're correlating. The null hypothesis would say there is no correlation between observations made by observer A and observer B. If you wrote difference, this would be wrong because a test of association doesn't look for differences in data. It looks for association, relationship, or correlation between two covariables. So if we have a look at our Simon Cowell table again, we're looking at a related design because the two observers are looking at the same data. It's a test of association because we want to see if the relationship between these two observers' data. And it's interval data because we're counting the number of observations. So the difference between observation, so say we're looking at number of hits if we're testing aggression in a playground, then the difference between 1 hit and 2 hits is going to be the same as the difference between 3 hits and 4 hits. Therefore, it's interval data. So therefore, it's a Pearson's R. Now for Pearson's R, there's another criteria that needs to be met because it's a parametric test, and it meets this criteria. So the data are interval because we're counting the number of observations. The populations are assumed to have normal distribution, and the third one is that the variances in the samples are assumed to be the same because participants are related. It's the same children or participants that the observers are. Step 2 is to place raw data in the table, and again in an exam this will always already be done for you. So observations from the two observers are placed in the raw table, observer A in one column, observer B in the other, and we have the behaviour on the left hand side, and they're just counting how many times they've observed that behaviour, and now we're going to correlate their two scores to test for inter-rater reliability. Step 3 is that we have to find the calculated value of R, and the formula for this is way too complex and you would never ever use it in an examination. You wouldn't even be asked to replace certain data from an equation like you would with the Spearman's row. It's usually used using an online calculator. So if a Pearson's R question comes up in the exam, they'll give you the R value. In this case, ours is 0.470. So is the result in the right direction? It is, because it's a positive number. If it had been R equals minus 0.470, then the the results aren't going in the right direction, because we would have seen a negative correlation between the two observations. Step 5 is to find the critical value of rho. And again, you would always be given this in an exam. All you need to know is the significance level, which in this case is 0.05. Whether it is a one-tailed or a two-tailed test. It's a one-tailed test. It's a directional hypothesis that we wrote because we said that observations from observer A and observer B were going to be positively correlated. And in Pearson's R, we look at degrees of freedom, which means that we don't take the n number as it is, we minus 2 from it. N number originally was 9 because there were 9 behaviours that we were observing, so we have to look for n equals 7. And now we just have to locate the rho on the statistical value that begins with our df value. So therefore our critical value is 0.582. Remember, our R value was 0.470. So our R is our calculated value, critical value is 0.582. It has an R in the title, Spearman's R. Therefore, the calculated value has to be greater than or equal to the critical value. In this case, it's not, it's less than. So now we just have to report the conclusion. If the calculated value is equal to or greater than this critical value, our result is significant, but in our case, it's not. Our calculated value was lower than our critical value. So then we would say, as the calculated value is not significant at p is less than or equal to 0.05, we must accept the null hypothesis and conclude that there is no correlation between observations made by observer A and observer B. Your last task is to have a go at this apply your knowledge question. So a researcher conducts a study to see if age at time of taking GCSEs and mean GCSE grade are associated. You can work out your average GCSE grade by adding them all up and dividing by however many GCSEs you took. A, identify a suitable test to use to analyse this data and justify your choice. So what this question is asking is, are you using a Spearman's rho or are you using a Pearson's R? You're obviously going to use a Spearman's rho because Pearson's R is only used when we want to assess inter-rater reliability, which is not what we're doing here. So you put that a suitable test to use would be Spearman's rho and you tell me the reasons why. So you look back at your Simon Cowell table and then tell me the level of measurement, what kind of design it is, what it's testing for, and that should justify your decision. Then B, the researcher calculates the correlation coefficient for 15 participants using a non-directional hypothesis. What calculated value would be significant at 2% level? So all you need to do here is have a look at this critical values table, find out what your N number is, so how many participants, what kind of significance level are you looking at, and what kind of is it a one-tailed or a two-tailed test, which it tells you right there. And basically what you need to do is find out what calculated value would be significant. So remember the significance of R. Spearman's rho has an R in it, which means that the calculated value has to be greater than or equal to the critical value. So whatever the critical value is that you find in the table, it needs to be greater than that, your calculated value. So you can basically write any number for that. And we'll go through the answers next lesson when we look at chi-squared and reporting investigations. As always, please upload your notes onto Teams, and any questions, please let me know.